page 306. We want to look at the second half of section 4.3. So we have gotten two introductions to the six trig functions. We've seen the definitions of the six trig functions in terms of a right triangle, in terms of opposite, adjacent, and hypotenuse. And we've seen the six trig functions in terms of the unit circle. So now we want to go back and see how we could use those trig functions. Now, the second half of section 4.3 is almost like a preview of coming attractions. They're going to go through and say, hey, let us show you some of the things that we're going to be doing in upcoming sections in much more detail. So they just kind of give us a brief survey of some of the things that we're going to look at in much more detail later on. So on page 306, they start us off with another table of formulas that we need. The first six formulas that you'll notice there on 306 are the reciprocal identities. Now, those reciprocal identities we actually already know. Like if you'll notice, it says that sine is 1 over cosecant and cosecant is 1 over sine. Basically, that's that same idea that we've been using as we list the six trig functions. We always put sine and cosecant right beside each other, because when we get our sine value, then we can just turn it upside down to get our cosecant value because they're reciprocals, right? So that's all they're saying right here. Sine is the reciprocal of cosecant and cosecant is the reciprocal of sine. Same thing with secant and cosine and tangent and cotangent. So we do need to recognize them in their formal definition form as you see there on page 306, but we actually know those already. Then they give you quotient identities there on 306. We learned those on the very first day, that tangent was sine over cosine and cotangent was cosine over sine. So we know those already. But the next three that they give you are called Pythagorean identities, and we don't know those yet, and so we want to be sure that we memorize those tonight along with those reciprocal identities. Even though we're already familiar with them, we want to make sure that we can recognize them in their formal definition form. So tonight you need to memorize your Pythagorean identities along with your reciprocal identities there on page 306. The three Pythagorean identities you'll see right here. Here's one of them. Sine squared plus cosine squared is equal to 1. Now, when we write sine squared, what we mean by that is the sine of theta, that whole quantity, squared. That's not the same thing as what you see here, where we just have the sine of theta squared, because in that case, only the theta is being squared. Here, the entire quantity sine theta is being squared. Here, only the theta is being squared. But what happened was people meant they wanted the whole quantity squared, but they accidentally wrote it this way. And so to avoid misreading, we rewrite it like this, where we've got sine squared theta. So that it's crystal clear, we mean that whole thing is supposed to be squared. So when you see the identities up here like sine squared plus cosine squared is equal to 1, that's what they're talking to. Take your sine value and square it. Then take your cosine value and square it. Add those together and it'll be equal to 1. Now, each of these three identities that you see listed here, you'll notice that they're an equation. You can turn an equation around in lots of different ways. And so just to kind of illustrate that for you, right here we've got sine squared plus cosine squared is equal to 1. If we subtracted this sine squared over to the other side, that'd be 1 minus sine squared is equal to cosine squared. So that'd be another way to write that same identity. Or if we come back to the original and this time we subtract the cosine squared over to the other side, that'd be 1 minus cosine squared is equal to sine squared. So there are lots of different ways that we can turn these identities around. They're equations, so you can add and subtract things over to each side. And so I've just tried to show you, even though these are the three identities, these are some of the alternate ways that you might see them given where we have turned the equation around. All right, so example number 4. Example 4 says, let theta be an acute angle such that the sine of theta is equal to 6/10. So then find the values of cosecant, cosine, and tangent using these trig identities that we just got on the top of page 306. Okay, so if I know sine, how can I find cosecant? What's the relationship between sine and cosecant? They're reciprocals, right. So if sine is 6/10 or 3/5, if we reduce that down, then what would cosecant be? 5/3, right, because I would just use the reciprocal. I would turn it upside down. So by definition, cosecant is 1 over sine. That means it would be 1 over the 3/5. So yes, I'm just going to turn it upside down and get the 5/3. All right, look at the next one. For the next one, they want me to find cosine. The only thing that I know is the sine value, and they want me to find the cosine value. So here's where I could use one of those Pythagorean relationships. Sine squared plus cosine squared is equal to 1. So if I know the sine value is 3/5 and I'm trying to find the cosine value, that would be the only unknown and I'd be able to solve for it. So remember what we said the definition was up here. When you see sine squared, that means take your sine value and square it. So our sine of theta was 0.6 or 3/5. So let's take that value of 3/5 and let's square it. So we're taking our sine of theta and squaring it. And then we're going to solve for cosine. All right, so if I solve for cosine, order of operations, I'm going to have to do exponents first. So 3/5 squared would be 9/25. So let's subtract that 9/25 over to the other side. And I'm going to combine. So 1 minus 9/25, I would have to do 25/25 minus 9/25. So 25/25 minus 9/25 is going to give me 16/25. And then to get cosine by itself, I'll take the square root of both sides. Now, typically when we take the square root, we insert a plus or minus, and we will do that in later sections. But for right now, they're not requiring me to consider whether it's positive or negative. That's going to be based on the quadrant that I'm in. They're not asking me to deal with that yet. So for right now, we can just deal with the positive value. All right, then we want to find the tangent. The only thing that I know right now is sine, cosecant, and cosine. So if that's all I know, how could I find tangent? What's one of our definitions of tangent? Sine over cosine, right. So I could go through then and say, okay, I know the sine value is 3/5 and I know the cosine value is 4/5. So let's do sine divided by cosine. So of course when we divide fractions, we keep the first one the same, we change the division sign to multiplication, and we change 4/5 to 5/4, multiplying by the reciprocal. Or you may have learned it keep, change, flip. That's right. Now, I understand the directions for this example specifically told us that they wanted us to use those trig identities on the top of the page. But if they had not specified that and they had just asked us to find these values, there is a much faster and easier way that we could have done that. If we go back to the first half of section 4.3 where we worked with triangles, all right? If I know that sine is 3/5, all right, sine works on a right triangle and it works on the acute angle of a right triangle. So I can draw a right triangle and I can choose one of the acute angles of that right triangle, and I can say, okay, for this angle, I know that its sine will be 3/5. Now, sine is opposite over hypotenuse, so I can say, okay, opposite will have to be 3, hypotenuse will have to be 5. So if they told me that the sine was 3/5, I could say, okay, if this is my angle, sine is opposite over hypotenuse, so opposite would be 3, hypotenuse would be 5. What's this other side going to be over here? 4, right. And I could get that by Pythagorean theorem, or remember we said we're going to see that 3, 4, 5 triangle all the time, so it's good for us to be able to recognize that and not have to do Pythagorean theorem to find it, but I surely could. All right, so if I just did that little bit of work right there and got that triangle, I still would have, to find cosecant, I still would have used the reciprocal of 3/5 is 5/3. But when I got right here to cosine, if I'm trying to find the cosine, I would have just come over to my triangle and said, okay, cosine is adjacent over hypotenuse. There's 4/5 right there, no work required, right? I wouldn't have to do any of this. Again, cosine is adjacent over hypotenuse, 4/5. There's my answer. Tangent is opposite over adjacent. So that would have been 3/4. There's my answer right there. I don't need any of that work. Okay? So it just gives me another way that I could do this same thing. Doesn't matter which way that you do it. It's nice to have some options, but definitely that would have been faster and easier if I had not been given those specific instructions to do it by the identities. All right, look at our next example. For example number 5, it says, use trig identities to transform one side of the equation into the other. Now, when we do this later on, we'll actually spend several days working on transforming one side of an equation into another, very similar to a proof. And so when we do that, we'll only be allowed to work on one side and modify it or simplify it down until it's equal to the other side. So while we're learning these now, it'd be a good idea just to go ahead and practice them in that way. So we are only going to modify one side until it is equal to the other side. So we're only going to modify one side until it's equal to the other side. In that case, when I'm looking at an example, I'm going to choose the more difficult side to simplify down to see if I can simplify it until it's equal to the other side. All right, so I'm going to start with cosine times secant and see if I can simplify that in some way. All right, I know that the definition of secant is that it's 1 over cosine. It's the reciprocal of cosine. So what happens when I multiply cosine times 1 over cosine? What do I get? 1, yeah. So I've modified that left-hand side, simplified that left-hand side until we got it to be equal to the right-hand side. All right, look at the next one. For the next one, I've got secant plus tangent times secant minus tangent is equal to 1. All right, that left-hand side is definitely the harder side. I want to try and simplify that down to get it to equal the right-hand side. I just don't even know where to start with that. Well, what confuses us is the trigonometry. So one of the strategies that we're going to use when we're working on these later on is we're going to say if it's the trig that's bothering you, just substitute it out. Replace it with something more normal, okay? So, for instance, if I went through and I replaced every one of my secants with x, and I replaced every one of my tangents with y. So all I'm doing is just giving myself something a little more normal. If they had given you x plus y times x minus y and told you to simplify that, you would immediately know what to do, right? What would you do? Foil it, right? That's just a difference of squares, right? So when you foil that, you would get x times x is x squared. A positive xy and a negative xy would drop each other out, and negative y times y would be negative y squared. So if I go back and I apply that same idea to our original problem, I'm going to FOIL this out. It's going to be a difference of squares. I'm going to end up getting the first term squared minus the last term squared. So if I FOIL that out, I'm going to have secant times secant is secant squared. Secant times negative tangent and secant times positive tangent drop each other out. And tangent times negative tangent is negative tangent squared. So that exact same thing that we had gotten when we did it with the x's and the y's, x squared minus y squared, the first quantity squared minus the second quantity squared, difference of squares, same thing. I've got secant squared minus tangent squared, the first quantity squared minus the second quantity squared. All right, so now let's see if we can simplify that down to 1. Well, if you look back up at the top of your page at your identities, the Pythagorean identities that we had today, you'll notice that there's one that has a secant squared and a tangent squared in it, right? That second one, 1 plus tangent squared is equal to secant squared. And if you look across at several of the different ways we noted to write that, one of them is secant squared minus tangent squared is equal to 1. So this secant squared minus tangent squared is equal to 1, and so I've modified my left-hand side until it equals my right-hand side. So we've basically proven that identity. All right, look at example number 6. Example number 6, they ask us to use a calculator to evaluate the secant of 5.67 degrees. Actually, in the textbook, it doesn't say 5.67 degrees. It says some kind of craziness in there, right? This is what it's referring to. That is 5 degrees, 40 minutes, and 12 seconds. If you were an architect and you were building a 60-story skyscraper, if you were off by half of 1 degree, it would be significant, right? So a degree measure, even though when we think of 1 degree, we think of that as just a tiny, minuscule little measure, when you expand that to the side of a 60-story building, 1 degree becomes huge, right? And so you have to have a way of being more precise than just a degree or maybe even half a degree or something like that. And so what they did was they treated a degree exactly like an hour on a clock. If you take a degree, you can break 1 degree down into 60 minutes, and then you can break each one of those minutes down into 60 seconds. And so this is 5 degrees, 40 minutes, and 12 seconds. We don't use those minutes and seconds nearly as often now that with the advent of a graphing calculator that can give me 8 decimal point accuracy. I have a way that I can be more precise with that. So when we come across one of those problems in the textbook, like if you have one of those in your homework assignment, I'm always going to omit it, or it's going to be in the every other odd that I skip around it or something like that. So we will not work with those, but I just wanted you to be exposed to them so you knew what that was referring to. All right? So if we were asked to find the secant of 5.67, we talked about this yesterday, about how to put that in your calculator. You do not have a secant, cosecant, or cotangent button on your calculator. So we said we would have to rewrite that using its reciprocal. So what's secant the reciprocal of? Cosine. So I would have to rewrite that as 1 over the cosine of 5.67. Is 5.67 in degrees or radians? Degrees. So you're going to need to make sure that when you type that problem into your calculator that it's in degree mode. Remember yesterday we switched our calculator to radian mode. As you're going through the homework, you're going to have to switch back and forth frequently. On tests and quizzes, you may have to switch back and forth frequently. So be careful that you pay attention to see, is there a degree symbol there? Okay, I need to be in degree mode. If not, then I need to be in radian mode. So remember, you hit the mode button on your calculator. It's on the very first row of your calculator. Hit your mode button, arrow over to degree, and hit enter. And when the highlighting changes to degree, then you're in degree mode. All right, so we're going to type that into our calculator. So type in 1 divided by cosine 5.67, and let's make sure that you're all able to come up with that 1.0049. Everybody getting that to work for you? Okay. All right, on the bottom of page 307, they give us a couple of bold print terms. Angle of elevation and angle of depression. In our next example, example 7, we're going to need to use this. So let's see what they're talking about. It says an angle of elevation denotes the angle from the horizontal upward to an object. All right, so let's say that we are standing on the ground and we're looking up to the top of a building. That angle from the horizontal upward to the top of that building would be an angle of elevation. Then it says that in other applications you may be given an angle of depression. An angle of depression denotes the angle from the horizontal downward to an object. So like if you're looking down into a subway or something like that and you're trying to figure out the angle that you would need to make those stairs to go down into the subway or something like that, you could have an angle of depression from the horizontal downward. So over on page 308, example number 7, it says a surveyor is standing 50 feet from the base of a large tree, as shown in our figure. The surveyor measures the angle of elevation to the top of the tree as 71.5 degrees. How tall is the tree? So, you think of some of these huge sequoias and some of these trees that are hundreds of years old. How do we know how tall they are? I mean, nobody climbs to the top of them and drops down a tape measure, right? If you're going down the highway, a lot of times you'll see like a crew on the side of the road, and there'll be a guy like there with like kind of looks like a tripod with some type of a camera or some kind of device on the top. Those are typically surveyors, and surveyors are used to help with architecture, and like we can see here, forestry, with road construction, engineering. I mean, there are just all kinds of applications for where this type of trigonometry would come into play. So we've got our happy little surveyor. That's sad, I know. But we've got our happy little surveyor. He is 50 foot away from the base of the tree, and he has to look up an angle of elevation of 71.5 degrees to see the top of that tree. So from that, they want us to figure out the height of the tree. When I look at one of these problems, the way I need to approach it is I need to figure out, what do I have? All right? I have this angle, 71.5. I have what is adjacent to that, and what I'm trying to find is what is opposite of it. I have this angle, I know what's adjacent to it, and I'm looking for what's opposite of it. So which one of my trig functions deals with opposite and adjacent? Tangent. Actually, tangent and cotangent, right? But I have a tangent button on my calculator and I don't have a cotangent button, so I'm going tangent. Right? So I'm going to use tangent then. So the tangent of 71.5 degrees would be equal to opposite. What's opposite? H over adjacent. What's adjacent? 50. So that's how I'll know which trig function to use to set it up. It's based on the information that I have in the problem. All right? So now we're going to get h by itself. So let's multiply both sides by 50. And then I can just throw that into my calculator. Degree mode or radian mode? Degree. So we were in degree a second ago, so we should already be set. So we can just do 50 times the tangent of 71.5, and we find out that our tree is 149.4 feet tall. Wow. All right, look at the next one. Example number 8 says, a person is 200 yards from a river. Rather than walk directly to the river, the person walks 400 yards along a straight path to the river's edge. Find the acute angle theta between this path and the river's edge as indicated in the figure. And they were kind enough to give us an illustration so we knew what they were saying. So we've got an individual 200 yards away from the river, but he doesn't walk straight to the river. He kind of walks on a diagonal path that is 400 yards long, and they want to know the angle between the river and the path that he took. All right, so to figure out which trig function I'm going to use, I'm going to look at my problem and see, what do I know? I know that I'm looking for this angle, I know what is opposite of it, and I know the hypotenuse. I'm supposed to find this angle, I know what's opposite of it, and I know the hypotenuse. So which trig function is opposite and hypotenuse? So that means I want to use sine, right? So I can say the sine of my angle is equal to opposite. What's opposite? 200. And what's hypotenuse? 400. So we could simplify 200 over 400 to 1/2, right? How am I supposed to put that in my calculator? Like, it gave me the answer and it wants to know the question. We're going to call these our Jeopardy problems. They told me when you take the sine of some angle, the answer is 1/2, and they want to know, what was the question? What was the angle that you took the sine of? I don't know. Well, sine is the same thing as y on our unit circle, right? Isn't that one of those values that we saw on the unit circle yesterday? Grab your unit circle if you would. I'm trying to find this angle right here. It is an acute angle. Acute angles have to be less than what? 90. So what quadrant am I looking in? Only in the first quadrant. where in the first quadrant do I have a sine value or a y value of 1/2? 30 degrees. That is my answer. So obviously, this was a very contrived problem, right? They would have only been able to ask me just a few things that would come up with a value that would be on that circle. Okay, so what happens if I have a value that's not on the circle? Like, what am I supposed to do if I plug in the values they give me here and I get something like sine is equal to 0.437? That's not on my circle. What do I do with that? Well, you remember when I told you that you had those buttons on your calculator that they looked like secant, cosecant, and cotangent, but they weren't? Okay, like that sine to the -1. It looked like it should be the reciprocal of sine, but it's not. It is the inverse of sine. It undoes taking the sine of something. On your calculator, if you will go second sine, okay, that's that inverse sine, that's that sine to the -1 that looks like it should be the reciprocal button and it's not. If you'll do second sine of 1/2, it'll give you that 30. We're going to call that our Jeopardy button, okay? So we'll use that sine to the -1, cosine to the -1, tangent to the -1. Those are going to be our inverses for sine, cosine, and tangent. Those are going to be our Jeopardy buttons. When they give me the answer and they're looking for the question, instead of taking the sine of the angle, I want my calculator to undo that. The sine's already been taken. I want you to undo that and tell me what it was before we took the sine. That's what they mean by the inverse, okay? So if it was something then like the sine of 0.437, that's not a value on my circle, I could put that in my calculator, right? So I could type in inverse sine or second sine of 0.437, and then it will tell me the angle 25.9 that I took the sine of that gave me that value. Now, sometimes they'll ask me to give the answer in degrees, and sometimes they'll ask me to give the answer in radians. It depends on which mode I'm in my calculator as to which I'll get. I type it in the exact same way. But if I typed this in degree mode, I would get 25.9 degrees. If I typed this in radian mode, I would get 0.452 radians. It's the same thing. It's just two different names for the same angle, one in degrees and one in radians. Okay? All right, so here is our homework for tonight on pages 310 and 311. Remember that we have our quiz tomorrow over 4.2 and 4.3. You are not using a calculator of any kind on that quiz. So that means that, like these word problems that we were just working on, if I gave you one of those, like this would be your answer right here, 50 times the tangent of 71.5, because you'd have no way to put that in your calculator. That would be what was in the multiple choice for you, okay? Or if it was a problem like this that was a value that you could get off of your unit circle, then yeah, we could go ahead and simplify it down. But if it was something like this that you could not get off the unit circle that you would need a calculator for, then your answer in the multiple choice would just look like this, because that's as far as we can go without a calculator, okay? So no calculator of any kind for your quiz. I will give you the outside of the unit circle, all right? What I mean by that is the unit circle that I gave you yesterday. Please pass that back. The unit circle that I gave you yesterday, I will give you the outside of it, the ordered pairs, but I have whited out the inside of it. There are no degrees and radians on the inside because we're supposed to know how to fill those in now, okay? So for your quiz tomorrow, I will give you this exact same unit circle, but the degrees and the radians will not be on the inside. I will only give you the ordered pairs on the outside, okay?